Hello, good people. Welcome to video number 3. We're continuing our work with the error of using a Taylor polynomial. That's not meaning to say that it's wrong to use it, but the error that we get based off of the comparison of the estimate with the actual number. How far is my estimate? That's what we're figuring out. And we're using the Lagrange error bound to figure out how that works. So if we read example 3, determine the degree of the Taylor polynomial expanded about the center c equals 1 that should be used to approximate the natural log of 1.2 so that the error is less than 0.001. All right, there's a lot going on here, so we're going to take it one at a time. We're definitely going to use a Taylor polynomial, but what's different here is I don't know how far to go. I don't have a degree. We're looking for the degree. As a matter of fact, we're looking to see how many terms do I need to write out so that my estimate has an error that's less than 0.001, less than a thousandth. So I want my error to be that precise. How do I do that? Well, I have to start with the Taylor polynomial to begin with, right? Because if I don't have the Taylor polynomial, then I don't know what this looks like. So let us begin. The degree of the Taylor polynomial P of n expanded about c equals 1, and we're going to look for the natural log of 1.2. So that should tell you that our original function is natural log of x. Our derivative function is a derivative of the natural log. And I'm gonna continue to take derivatives. Now, remember, normally we know what degree to go to, we know where to stop, but in this case, I don't. So I'm gonna go, I don't know, maybe 4 derivatives, maybe 5 derivatives. I don't know. Let's take the derivative of 1 over x. That's negative 1 over x squared. Let's take the derivative of negative 1 over x squared, which is positive 2 over x to the third. Let's take the fourth derivative. We put a little 4 in parentheses. That's the fourth derivative. Let me zoom in a little bit so you can see it a little bit better. That'd be negative 6 over x to the fourth. And then the fifth derivative, which is a 5 inside the parentheses here, the fifth derivative of f would be positive 24 over x to the fifth. All right, so I did 5 derivatives. So I'm going to write out 5 terms. That doesn't mean that I need them all to get within less than a thousandth. As a matter of fact, I don't know how many I need. I might need more. But we're going to go ahead and evaluate this to figure out the Taylor polynomial for 5 terms, 6 terms up to the 5th degree. So let's see, f of, now wait, what number am I supposed to substitute? I'm supposed to substitute my center. So my center is 1. So the natural log of 1, that's 0. And then f prime of 1, that's 1 over 1, that's positive 1. F double prime of 1, that's negative 1 over 1 squared, that's negative 1. And we continue to substitute 1 into each of these derivative formulas. We're trying to see what kind of coefficients we're going to get when we use the Taylor polynomial. Negative 6. And the fifth polynomial would be positive 24. Do you notice how, because I'm substituting 1, because my center is 1, all my denominators really just vanish, and I'm left with the numerator values. And as I look at the numerator values, I kind of see a familiar pattern. And if you don't see it, 1 times 1 is 1, 1 times 2 is 2, 2 times 3 is 6, 6 times 4 is 24. So the next one I would multiply by 5. What I'm really looking at here are factorials, right? The factorial, 4 factorial is 4 times 3 times 2 times 1, that's 24. 3 factorial is 3 times 2 times 1, that's 6. Hey, these are where the numbers are coming from. At least that's the pattern that I think I see. Great, so let's build what the Taylor polynomial would look like, even though I don't know how far it's going to go. So this is going to go to, let's see, start with the function value at 1, and that's just 0, plus the Taylor polynomial formula says take the derivative value and then multiply it times x minus my center, okay? And then and the first one I don't have any division. And the next one, plus take my second derivative value over 2 factorial times x minus 1 to the second power, plus, take the next one, 2 over 3 factorial times x minus 1 to the third power, and so on, right? Plus negative 6 over 4 factorial times x minus 1 to the fourth, plus 24 over 5 factorial times x minus 1 to the fifth. Now, this will continue to go on up to the nth term. Now, the nth term, let's see if we can figure out a formula for the nth term. Um, it would be x minus 1 to the nth, right? Because my exponents are just increasing by 1. And then I notice that this factorial in the denominator is the same number as my power. So this would be over n factorial. But what I also notice is this numerator value. This is 4 factorial, this is 3 factorial, this is 2 factorial. So it looks like the top, the numerator, is n minus 1 factorial, n minus 1 factorial. And then the other thing I notice is that there's an oscillating behavior here. I have a positive, a negative, a positive, a negative, a positive, a negative. So I'm going to create a little device here, and I've run out of room because I started backwards. So I'm going to try to sneak it in. Negative 1 to the something power. Now, how do I know which way it goes? Well, when n equals 1, because this is 1, I get a positive term. So if n equals 1, that means my exponent, if I were to just put a 1 here, negative 1 to the 1 is a negative, but I don't want a negative. So let's do plus 1. And now when I substitute a 1, when I add it to another one, it'll give me squared, negative 1 squared, that's positive. Okay, and when I plug in n equals 2, that would be negative 1 to the 2 plus 1, negative 1 to the third, which is going to give me a negative term, and that's exactly what I have, a negative term. And if I substitute 2 in here, 2 minus 1 factorial is 1, 1 factorial is 1. Okay, I think I'm getting the pattern here. So I think this, and by the way, when I say think, I mean it is, this would be the nth term of this polynomial. Okay, but what are we looking for? We're looking to see when my error is less than 0.001. So how do I figure that out? Well, how do we usually figure out the error? So my remainder for the nth term, and I'm going to say this is at 1.2, right? That's the x value where we want the remainder. It has to be less than 0.001. But what was the formula for this? What did the Lagrange error bound tell us? That this had to be the maximum, not the man, the max of the n plus 1th derivative evaluated at some z times x minus c to the n plus 1 divided by n plus 1 factorial. Okay, so I think I got it. Now, where do we go from here? Well, I need to figure out the maximum value of the n plus 1th derivative, right? That would be nice if I could take care of that. Oh, wait a minute. The n plus 1th derivative, did we figure out a pattern for the n plus 1th derivative? Remember, the n plus 1th derivative were these numbers. This is the n plus 1th derivative. And in my nth term, that equates to this. Well, actually, this is the nth derivative. So I should say f prime, or I'm sorry, f to the nth derivative is equal to n minus 1 factorial. Right? Because n factorial on the bottom is part of the Taylor polynomial equation. And then x minus c to the n, that's part of the polynomial equation. This, oh, well, I guess I need to include that, don't I? Negative 1 to the n plus 1 times n minus 1. That's where the derivative comes into play, because the derivative came from these numbers, right? The derivative values came from these numbers, and this formula is what created those numbers. Oh, but I want the n plus 1th term. So then that's going to be uh, n plus 1 plus 1 times n plus 1 minus 1. What did I do? Wherever I saw an n, I substituted an n plus 1. Okay, so that equals negative 1 to the n plus 2 times, well, here the plus 1 and the minus 1 are going to cancel, and I'm just left with n factorial. So what I have right here is the n plus 1th derivative formula. So I come back over here, and I remember that all of this is inside the absolute value, right? So if it's inside the absolute value, when I write the maximum of the f of n plus 1 derivative, I can say, well, this is not really, and by the way, I'm going to go ahead and figure this out. This is 0.2 to the n plus 1. I really don't need to worry about this part, because when I take the absolute value, whether this is negative or positive really doesn't matter, because when I take the absolute value, it's going to go away. So I can kind of ignore that, because eventually it's gone. And then on top of that, I notice I have an n factorial divided by n plus 1 factorial. That means that I have just n plus 1 on the bottom, the denominator, because all those factorials are going to cancel with all of them except n plus 1 term. And then on the numerator, I still have this. I want this to be less than that. And because n values are always positive whole numbers, and I don't see any other um, negatives that could appear, I can take away the absolute values, and I can say, this is what I need to solve. All right. Now, wait. There is a question. Why was I able to replace this with this? Well, we found a formula for the nth derivative, and therefore we found the formula for the n plus 1th derivative, and I was able to just plug that in to replace it. Now, how do I know it's the maximum? Because z should be between my center and my x value. So z has to be a value between those two, according to the theorem. However, when you look at the derivatives, I can tell that the way I'm working this, I'm always going to have a maximum number occur at the next derivative value. And so by just plugging that in, I'm able to guarantee that this is a pretty good replacement for the maximum derivative value. Great. So now I get to this. Now what? How do I solve this? Well, there really isn't a way, because I have n's in the exponent and n's in the denominator. So the next best thing I can do is guess and check. So what if my n value is 2? What if my degree of my Taylor polynomial is 2? Is that going to be enough? 0.2 to the 2 plus 1 over 2 plus 1. Is that less than 1,000th? That's the question. Because if it is, then I only need to go out to the second degree polynomial of the Taylor expansion. Well, let's see. Go to my calculator. Let's clear that log. And we said, what happens if we do 0.2 to the power of 2 plus 1 divided by 2 plus 1? Is my answer less than 0.001? No, it's not. All right, well, what if I go out an extra term? What if I go out to the third degree polynomial? 0.2 to the 3 plus 1 over 3 plus 1. Is that less than, that's a question mark, is that less than 0.001? So I go back to my calculator. To save time, I'm just going to copy paste and then change my 2 into a 3. So this is telling me, what if n is 3? What if I go to the third degree Taylor polynomial? I get 0.0004. 0.0004. Is that number less than 0.001? Yes. So therefore, in order to get an error that's less than 0.001, I need to go to the third degree Taylor polynomial, to the term that ends in 3. I need to stop right here. Here. This would produce an answer that is accurate or whose error is less than 0.001. And that's how we can use the Lagrange error to gain the accuracy that we are looking for.